All right, so what graphical kinematics is basically talking about is our ability to read position versus time, velocity versus time, acceleration versus time plots. So for starters, let's talk about position versus time plots. So here I've got, and again, we're thinking of one-dimensional motion here. So I've got position in x on the vertical axis. I've got time on the horizontal axis. So this is position versus time. And here's just showing some object as it moves back and forth in a straight line. So again, this is not x versus y motion here. This is just showing you where an object is as it moves back and forth across some line. Well, the first thing we can talk about is we can talk about sort of, again, the average version. So again, thinking about our average quantities. And basically, if you look between 2 points, pick any 2 points. Here we'll happen to pick this time t1 and this time t2. And so by looking at what the value of the position is at t1, what the value is of the position t2, subtracting x1 minus x, or x2 minus x1 over t2 minus t1, that's actually going to give you the average velocity. So notice that the line that connects those 2 points, so running from whatever the position is at t2 to whatever the position is at t1, the slope of that line, it's called the secant line, and that's going to be the value of the average velocity. Well, we know that if we make delta t smaller and smaller and smaller, so basically that says instead of t2 being way over here, you start bringing t2 back towards t1, and as you do that, in the limit of making that delta t effective, or in the limit of making that delta t 0, we end up with a derivative. And so again, here's a situation where our derivative equation tells us that the instantaneous velocity is the derivative of x with respect to t, and graphically that's the slope of the tangent line. So what you would do is you would say, hey, here is my curve, and here at the point t1, this is the tangent line to that curve, and the slope of that tangent line, right, y equals mx plus b, so the slope of that line at the point t1 is going to be the same as the instantaneous velocity at t1. We could play the same game at t2, and again we notice that as we take the tangent line to our curve at the point t2, it happens to be perfectly horizontal, which means that the velocity at t2, since it's equal to the slope at t2, and this point is going to be 0. So this is a point where actually our object is in the process of turning around, right? It's stopping to turn around. So it was moving in the positive x direction, larger and larger and larger and larger x values, but at this point it stopped to turn around and start moving back towards the origin. So our graph makes sense that at this point, t2, where it stopped to turn around, it has gone as far away from the origin as it's going to, and now it's going to start coming back. Velocity versus time plots. Well, again, we can think in terms of the average version, and we can think in terms of the derivative version. So with the average version, thinking between 2 points, well again, so that's going to give me the v2 minus v1 divided by t2 minus t1, and so that's just the average acceleration value. And graphically, again, what that means is that the average acceleration is going to be equal to the slope of the secant line on a v versus t plot. The derivative version says, hey, if you want to know what's going on at one point, well again, pick your point, here t1, draw the tangent line to the curve at that point, to your velocity versus time curve. So this is now showing the speed of an object as it moves. So the tangent to the velocity curve at some point t1, the slope of that line is going to be equal to the acceleration at that point. Again, pick a different point, t2. Whatever the tangent line is at that point, t2, the tangent line to your velocity curve, the slope of that line will be the acceleration. So graphically, the acceleration is the slope of the tangent line in a velocity versus time plot. So basically, if you're interested in figuring out these kinematical values graphically, here's basically what you have to do. If you want to know the position, just go read it off of an x versus t plot. That's the only option you got. If you want to know the velocity, now you got two options. You can read it off of a velocity versus time plot, or you can calculate the slope of the tangent line on a position versus time plot. If you want to know the acceleration, you got three options. So you can read it off of an acceleration versus time plot. You can calculate the slope of the tangent line on a v versus t plot. Or you can calculate how the slope is changing, what's known as the curvature, of an x versus t plot. And this is one of the things that we'll focus on a lot when we're thinking about acceleration. Is in one-dimensional motion, our acceleration means that you're either speeding up or slowing down. And so speeding up is a way of saying that the slope is getting steeper, right? Because the steeper the slope is, the faster your object is moving. And that doesn't matter whether that's a steep positive slope or a steep negative slope. So speeding up, an object is speeding up when the slope is getting steeper on an x versus t plot. Or if you're looking at a velocity versus time plot, when you're moving away from the t-axis. Again, it doesn't matter whether you're moving away in the positive direction or away in the negative direction. In either of those cases, your object is speeding up. Your object is slowing down when either your slope is flattening out on a position versus time plot, or you're moving closer to the t-axis on a velocity versus time plot. And so again, we'll look at some plots in class and really try and make sense of these in terms of figuring out what's going on with the position, velocity, and acceleration from looking at position, velocity, and acceleration graphs versus time.